Our next speaker is Dr. Craig Benson. Craig is the Dean of the School of Engineering and the Janet and James Hamilton Endowed Chair in Civil and Environmental Engineering in the University of Virginia. Prior to his appointment at UVA, he was a Wisconsin distinguished professor of Civil and Environmental Engineering and Geological Engineering in the University of Wisconsin-Madison. He has a bachelor's degree and also a master and PhD degrees, the latest degrees from the University of Texas at Austin, all in civil engineering, with emphasis in geo-environmental engineering. He has been conducting research and consulting related to environmental protection for 3 decades. He's recognized as the foremost international authority on engineered barriers for waste containment, and is widely sought after for his expertise in design and performance assessment. Especially for disposal facilities containing low-level waste and the uranium mill tailings. He leads the Landfill Partnership for the U.S. Department's Consortium for Risk Evaluation with Stakeholder Participation, CRESP, which provides research and technical support on issues related to performance assessment for low-level waste and mixed-level waste. He's the former editor-in-chief of the Journal of Geotechnical and Geoenvironmental Engineering, past president of the SCE Geo Institute, past chair of the GI Geoenvironmental Committee, past vice chair of executive committee, and several other committee assignments. Dr. Benson is a member of the National Academy of Engineering. With that, Craig.
Thanks, Mike. Very nice. I have to stand in one place. I like to walk and talk, but today, since we're using a video, I had to stand here. We're going to switch gears a little bit and talk about things at the top. Radon fluxes out of uranium mill tailings disposal facilities. This is my talk will be very application oriented, and one of the things I like about this group is this is what I call a get stuff done group of people. Everybody here has real projects with activities that actually have to get done at some point, permits that have to be created and approved, and facilities that have to be built. And I think that's where we want to be in the end anyhow, is actually getting things done, protecting the environment, and moving forward with restoration activities. We've been working for the last 15 years at trying to understand how systems evolve over time, how waste containment systems evolve over time. We make predictions in PAs out 1,000 years, 10,000 years. And we often base that on many assumptions about what properties are without data to support those assumptions. And we've been trying to fill in the blanks, you might say, about how those engineering properties change over time. We did a lot of work early on looking at hydraulic properties as a byproduct of a applied research program that we did on the hydrology of cover systems, and we're still working in that area, but we've transitioned some of that work to look at not hydrologic properties, but gaseous fluxes, the gas transmission properties from cover systems, which has been an area of concern in a number of projects in recent years, and that's what I'm going to talk about today. Can you advance the slide? I guess I don't have any control over the clicker. All right. Yeah, thank you. So just as an example, we're going to talk largely about uranium mill tailings disposal facilities. And we selected those, one, because they were of interest to some of us in our group. For example, NRC has a great deal of interest in this. But they're also a great analog of longer-term performance, because many of these facilities have been in place 20 or 30 years. And as we go back and look at them, we get a snapshot in time of essentially how the properties have, or the engineering behaviors evolved. And this is an example of a uranium mill tailings disposal facility. They're large disposal facilities in scale, like many of the different projects that we see in both NRC-related projects and DOE-related projects, large-scale disposal facilities, hundreds of acres in some cases. In this case, we've got a cover system over the disposal facility that's a mixture of a vegetated area you can see in the middle area where it looks like almost like a golf course, but I guarantee you it's not a golf course. And then a riprap, which is kind of that white area, which is a rock cover, meant for long-term erosion control. And these facilities are meant to be in place essentially in perpetuity, designed for a minimum of 1,000 years, analyzed for at least 10,000 years, but expected to last essentially forever. You get the next slide. And the question is, how do we predict how these facilities are going to function over time? And so we're interested. We start off as built down there at near time zero, and I have that as a blue star. We make measurements. We have lots of test methods we developed to do that, design procedures, and then we need to predict how that property or engineering characteristics going to change over time. And we have some models that are to do that, but the best thing we need, or the best thing to do, is to actually collect data that allows us to chart that change in property or engineering behavior over time. So as I mentioned, about 20, it's amazing, everything in life seems to have gone so far. You know, I used to talk about a few years ago, now it's like 2 decades ago. But we actually started this program called the Alternative Cover Assessment Program in 1997. In fact, I can remember a meeting like this, a seminal meeting when we started it, and it was 20 years ago. And as part of that study, we built large-scale test facilities around the United States to evaluate the hydrology of cover systems. And when that study had matured, we went back and exhumed all those cover systems and evaluated how the properties of those materials had changed. And that was a 5 to 10 year window. And so we were able to get up to 5 to 10 years, and that's my yellow stars on that chart. And really what we're trying to do now is to take another step in that process, and not just to look at hydrology, but to also look at gaseous emissions as well. So if you could just click the slide. And so our what I would call our Radon Flux project, we're right in the next log cycle, the 30-year time frame roughly in the middle of that cycle with our uranium mill tailings projects, which some were done in the 70s, many were done in the 80s, and then in the early 90s, and some are still being done today. And then the question is ultimately, how do we get out to our 1,000-year or 10,000-year projections, and how can we use analogs to get to that point? One of the things that we are doing, I'm not going to talk about this in any detail today, but as we work on our mill tailings disposal facility evaluations, we're looking at analog sites in the areas at the exact same time. So when we're studying the disposal facility itself, we pick an analog right by that facility that has the same type of cover profile, but in a natural earthen environment. And we're studying that too to give us that long-term projection. I won't talk about that today, but I expect in about a year, 18 months, we're going to have a lot of interesting information about how we can go from that red star to the green stars based on analogs. So next slide. So this is a typical cover profile used at a uranium mill tailings disposal facility. The intent early on in the original act on this was largely to control radon flux. Later on, the emphasis on controlling percolation into the waste became a priority as well. But it's important to kind of understand that the primary starting point was radon flux, or essentially gas movement up out of the facility into the atmosphere. And so at the bottom of this facility is a low permeability radon barrier. But originally a radon barrier primarily, and then became a low permeability radon barrier to control both water flux and gas flux. This is a fine texture barrier, typically a clayey barrier with high water saturation. So we're compacting it at water contents near optimum or above optimum to get the water saturation up above 80–85%. And the reason for that is so that the radon gas that's being generated below is transmitted very slowly through that radon barrier because of the low gas diffusion coefficient of that fine textured material. It holds a lot of water. Water transmits radon very slowly. If we have a water-saturated material or nearly saturated material in that radon barrier, the radon flux will be quite low. And actually, I'll show you some data. You can really see the really significant reduction in radon flux that you get across one of these barriers. Of course, that all depends on whether that barrier stays in good condition. Over top of that, we'll typically have what's called a protection layer. Today we often call it a frost protection layer, but it's just a thick layer of soil meant to provide some separation from the atmosphere. A bedding layer, and in many cases these facilities have riprap on top. The intent originally was to minimize erosion by putting essentially a rock cover on top. Some will also have a vegetated surface layer, and the one we'll look at in particular from Falls City, Texas, actually has both types of cover surfaces in place. So today, as I mentioned, both of these functions are implicit in these cover systems, controlling both radon flux and infiltration. We use that barrier layer with high water saturation, low radon gas diffusion to manage both hydrology and gas flow. And the surface may be vegetated or it may be rock. So we'll see both of those. And I want to thank, this is the drawing that Jody Waugh made, and I use it over and over again. He deserves some credit for this. And I guess I should say one more thing before I move on. This project, while I'm presenting it, is actually a very collaborative project. It's EM, it's NRC, it's LM, all working together. And Jody Waugh from LM and his team is part of this. We're representing EM through CRESP. We have folks, Mark Furman from NRC, involved as well. We have about 6 different investigators working on the project, and I'll show the list of those at the end. So a very collaborative project. Next slide. All right. So one of the things that made us think about, well, what are the impacts of long-term pedogenic change or soil structure formation due to natural processes on radon flux is what we observed in other cover systems. And I just show you an example here. About maybe 10 years ago now, it's hard to believe, we do everything in decades, we had the opportunity at the Monticello disposal facility where before the disposal facility was built, some large caisson lysimeters were constructed to look at the long-term hydrology. And when we were doing some exhumations at the actual Monticello disposal facility, we went back and exhumed these caisson lysimeters, which were about 20 years old. And we went all the way down through those profiles, a couple meters deep, and we're looking at the structure of the different layers. And one of the things we were able to do that is look at that radon barrier that had been in place about 20 years in that caisson lysimeter. And this is a photograph, one of the things that we observed. So this is down 1.9 meters. This is deep, all right? This is, up here, all right? Maybe it's 2 meters, about 6 feet. So right around, I'm just under 6 feet. So right around my height. That's 6 feet underground. That's the radon barrier. We see roots in it. We see it's dry. It has a crack. Its hydraulic properties probably have changed significantly. Whether that changes the gas transmission characteristics is another issue. Can you hit the next slide? We do know that the hydraulic properties of most barrier layers evolve over time. They tend to become more permeable and they kind of level out into a range. And this is an example of what we found looking at the hydraulic properties of clay barrier materials in cover systems. And this is a graph here from a number of different field sites around the United States looking at the in-service hydraulic conductivity after it's been in service for 5 to 10 years versus the as-built saturated hydraulic conductivity. And if no change had occurred, all the data would fall along that one-to-one line that we see going up and down the middle. But what we see is the data actually fall above a band that's anywhere from about 10 to 1,000 times more permeable than the initial condition. And in fact, the least permeable barrier materials tend to change the most, and most of the data end up, regardless of where they started, in a band that's essentially independent of the as-built saturated hydraulic conductivity. We see that change in hydraulic properties in barrier systems, and we can design around them. We do a PA, we can incorporate that into our assessment and do the analysis so we predict that type of pedogenic change and its impact on hydrology. The question is, do we see the same thing when we look at gaseous fluxes? Do we see the same changes in the diffusive properties of these materials? And that's what we're after with this particular project. Go to the next slide. One of the other factors that drove some of our interest in this is there have been a couple of other studies. This one shown, for example, where multiple measurements had been made at previously constructed facilities to evaluate radon flux post-construction. And some of those studies had indicated at least that there was a greater degree of variability in the fluxes than was anticipated based on the post-construction information. Now, whether that's actually true or not, one of the things that we've learned in radon flux measurement, there's a lot of details to making those flux measurements properly, and a lot of error can creep in. So having a high degree of variability could just be due to experimental error as well. But that was one of the motivations, is that there was some concern about some of these higher variations in radon flux than had been observed historically. Next slide. But what we do see, as we look at radon barriers, is we do see pedogenic change. And I'll show this slide again a little bit later. But we get to look at radon barriers in actual facilities that have been in place 20 or 30 years. We do see that the barriers are changing. They're evolving. These are just some examples. This is a Shelby tube on the left taken from a radon barrier where a mesquite brush was growing over top, all right? And you can see that woody root going right, we got pure luck to get that root right in the middle of the tube. You know, pulling the tube apart and you get this root and it's actually going right down the middle of the tube, but that's right down through the barrier, all right? What are the impacts of that? Well, we can measure that. And on the right, you see this actually a larger piece of material, but you can see all the fine roots in it. And those roots are extracting water during the times of the year when evapotranspiration is significant. That causes shrinkage and swelling of the material. You can also see iron oxides on the surfaces, so there's some structure in that material, and there have been oxides that have deposited on that material. They're probably important hydrologically. Whether they're important from a gas flux perspective is another issue. That's one of the things we want to get at. Next slide. So the way we went about this, we're making radon flux measurements, and the first thing that we did was actually go back and really look at all the radon flux literature and develop in our laboratory a series of tests to make sure that the methods that we were going to use in the field had a high degree of reliability. We came with a strategy actually using two very different methods to measure radon flux simultaneously, so that we had essentially two independent measurements. We use a chamber, essentially putting a large dome over the barrier system in which the radon emanates up through and collects in the chamber, and we measure the radon that accumulates. And that's shown schematically here. We see essentially have a box here in the middle. That box has two things in it. One, a little canister, that's that small rectangle in the middle. That's a canister that's got a container of activated carbons. So we're using a sorbent to sorb the radon. We collect it over a period of time, and then we analyze how much mass of radon has been sorbed onto the activated carbon. Another technique, which actually we like a lot better, is a more active technique where we're regularly sampling that gas that's in the chamber with an alpha tracker and measuring alpha directly with the tracker, and getting that essentially time-dependent measurement of a concentration accumulation in the flux chamber. And we'll look at a little comparison of those two. The carbon method is a traditional technique, and the alpha tracker is a more modern technique used in a lot of building systems, but it actually has a lot of opportunity here. Yeah?
This is done on the actual cover. Have you looked at the potential that putting the box on the cover will distort the flux? That an assumption that
Yeah.
Matt, I need you to come up here.
Oh, yeah. Well, I'll just repeat your question so you don't have to come up. But the question is, you know, when you put the chamber on, do you alter the system? You've essentially altered the boundary conditions, right? You have to account for that. And we actually use in the analysis, we use a back diffusion solution that accounts for that change in boundary. You have to do that or you'll get a misleading answer. He's my plant in the audience to ask some of those good questions. Thank you. Next slide. So we use this technique. You'll see some pictures of this. This is just a schematic of the alpha tracker that we use, this RAD7. We had a whole army of these RAD7s in our lab and then in the field. Really nice device. This one's got a strip chart recorder. That's a little old school. But you just plug these into your PC and download all the data digitally, and you can get a complete record of from the alpha tracker during the experiment. Yeah. And that's just a photograph of what the activated carbon canisters look like. These are like the ones you put in your basement. If you've ever sold your home, you have to do a radon test. It's not a lot different than that. It's got activated carbon. It's got a porous container. And you let it sit for a period of time, and then you seal it up and send it off to the lab and get the radon that's been absorbed onto it. Go to the next slide, too. We start off, I mentioned, in the lab, doing very controlled comparative tests with our different measurement techniques, so that when we went to the field, we were pretty confident that we were going to get high-quality data. When you go to the field, it's a huge time and expense, and you want to make sure that everything works. And we did a series of controlled tests with a source, a radon source that was highly reproducible for us, Wisconsin red granite. We have a good source of that in Wisconsin for us. It's crushed. Its radon emission properties are very well known, and we used that for a source in all of our laboratory experiments. And we were actually able to try all of our experiments that we did in the field. We mocked them up in the lab and did them at full scale. So we felt pretty confident when we got out to the field. Well, before we leave this, again on the left, that's the activated carbon canister, that red granular material. That's our Wisconsin red granite. On the right is the flux chamber that we would, one of the flux chambers that we would install in the field. It's just essentially a plastic dome, and it's got the alpha tracker on it. It's got some tubes that come in to allow us to pump the gas in and out. If anybody knows what that dome looks like, has anybody used one of those? I've heard lots of hydraulic conductivity stuff today. That's a sealed double ring infiltrometer interior dome, measured for field hydraulic conductivity. Now it's a radon flux chamber. We just give it a different name, all right? Go ahead, next one. Okay, it's a typical data. Getting back to this question about boundary conditions, it's what's called a radon buildup curve. So if you had an open surface on top of the radon barrier, we would have a free flushing boundary. We would have essentially zero concentration, and we'd have a steady flux. We put a dome on top. As gas accumulates in that dome, the concentration's increasing, and the gradient driving diffusion is diminishing, and we need to be able to account for that. The red dots there are measurements from our alpha tracker. The early flux here that you would see, the dashed line, is essentially the free flux without a constraint on the boundary condition. So that initial slope actually is the radon flux that we want to measure. That's also a difficult thing to measure just from the early time data, because that data set in the early part can have a lot of uncertainty about it. So we use this analytical solution, which I show on the top here, and I won't go through all the parameters, and we fit it to that radon buildup curve, and that accounts for back diffusion, accounts for decay, it accounts for losses, and then we can back calculate from that fitted curve what the initial flux is, J naught, and we use that as our radon flux. Go ahead, next slide. Just one thing I want to mention, while we're doing all this field work, we're doing a set of complementary laboratory work at the same time. I won't talk about some of those outcomes today, but we've used a lot of these same techniques with the alpha trackers on both the influent and the effluent, and flexible wall permeameters, like we heard on the last presentation, adapted for radon flux measurements. And so probably, hopefully next year I'll come back and talk about what we found from that. Next slide. And this is what one of those looks like one of your cells, just very creatively adapted like you had done for your experiments. Yeah, go ahead. Okay, so let's look at some field data. We've got 5 sites we're looking at. I'm going to show you the data from the first one that we did last spring. We did another one this summer. This one's in Falls City, Texas. This is where you get sent when you've done really bad things. You get sent to Falls City, Texas. Hopefully nobody's from Texas here. This is our first site. We picked this for a number of different reasons. You can see it was built in 1994, so it's got over 20 years of history in it. It's got more than 7 million tons of dry tailings in it, dry tons of tailings, and about 1,300 curies of radium. We did a site last summer at Grants, New Mexico, and we're looking at 3 other candidate sites right now to do in the upcoming year. Next slide. The cover profiles at Falls City and the top deck, this was a top deck was all vegetated. And I'll show you a slide of this in a minute. intended to have grass on the top. It's got essentially a topsoil layer, a growth medium, so about 3 feet of superficial layer. Then it's got, and that includes a protection layer in it. It's got a radon barrier that's 3 feet thick, and then beneath it, it has what's called a thorium layer. We're not quite sure what that is. It's this layer that's got some thorium waste in it. I know that sounds a little scary when we talk it up. We had rad techs there. We had good health and safety the whole time. And all of us wore dosimetry, and so we were safe. And then below the thorium layer was essentially windblown. This is just contaminated debris. So imagine they filled this disposal facility with tailings during operations. And then when they were restoring the site, they had all this contaminated soil around the facility, scooped it all up and put it on top of the tailings. Actually, it provides a nice working platform for building the other parts of the facility. This thorium layer was something they placed at the very end and then built the cover on top of it. That's the top deck. And then the slopes are just tailings, radon barrier, and then a bedding layer and riprap, so more closer to the surface. Go ahead to the next slide. So this gives you a picture of the two different textures, the rock on the left, the grassland on the top, on the left, excuse me, rock on the right, grassland on the left. That's top deck on the left, slope on the right, gradual slopes. Notice in the middle, so we've got grassland, but we have woody species that have come in. Not intended, but this is what nature provides. And we find this all over at this, even in rock covers that are intended to have no vegetation that get spraying regularly to control the vegetation. They have woody vegetation that has evolved in the rock cover. That's mesquite right in the middle. So we actually went in and did some of our tests right on top of where that mesquite had developed. We actually did one in Grants, New Mexico, where we did it right on top of a large ant colony within the radon barrier this summer, which is interesting petagenesis experiment. Next slide. So you just see there's some contrasting surfaces at this site, which is one of the reasons we picked it. We had a relatively typical thickness for the radon barrier. Some of these sites, for a lot of different reasons, they'll have a radon barrier that's 15 feet thick. Maybe because they had a lot of earth to move, all right, and they could place it. So we wanted something that was reasonable, and then we had higher than typical activity in the tailings. We wanted to make sure we had enough source that we would be able to measure something. So our first site, we wanted to put things in a condition where we'd actually come out with some positive outcomes. Next slide. We did 6 test pits at this site, 4 in the top deck, 2 in the side slope, and on the top deck we did them in grassland and then grassland with mesquite brush. All right. Next slide. And this is just an example of the different experiments going on. Top deck, you can see we've zoomed down through the protective layer. And we're right on top of the radon barrier here. It's Nick Stefani, the graduate student who did the work. Our large flux chamber, that's the big white box, right to the right of Nick. And then some smaller flux chambers to the right of that. And you can see these are kind of creative. The medium-sized ones made out of a big luggage container, and then the others out of PVC end caps. Like a lot of geotype experiments, we use creative materials to make our devices. On the bottom, on the left, is experiments getting ready to be done on the rock slope. And then on the very right is when we got done doing our work on top of the radon barrier. We excavated all the way down to the tailings and did a source measurement. And we want to do that for some of our modeling. And I'll show you some data comparing the source and then on top of the radon barrier in the next slide or so. Next slide. These are the different sizes of the chambers we used. We were wondering if we'd see scale effects. On hydraulic properties, we see a lot of scale effects because the network of pores that are controlling water flow, which is predominantly through the largest pores, is dominated by essentially the scale, the measurement. We wondered if the same thing was true for diffusion measurements as well. Next slide. So again, it gives you a little closer view of the different scale measurements from very small, lower right-hand corner. You can just see that white cap, that's 6 inches in diameter, up to this white box, which is 4 feet by 4 feet. Next slide. And here's an example of a radon buildup curve, test pit 1 at Falls City. The red line from the large chamber and the green triangles are on the surface of the tailings. a lot of reduction in flux by that radon barrier. It actually works really, really good. Should not surprise you. Has pretty high water saturation. It's fairly thick. Do basic physics on that, you should get a lot of reduction in flux, and in fact, we do. You can see the really dramatically different radon accumulation in those two different curves. Next slide. So let's look at some of the summary of the fluxes, and I put a red line up there at the regulatory standard just to give you a sense for where things are. One of the things that we found when we look at hydraulic properties, they vary a lot, and the percolation that we get varies a lot depending on how much petagenesis has occurred. We don't see that in the radon fluxes. We get a lot or little radon flux, and we still get a lot of or modest or a lot of petagenesis, and we get relatively modest changes, if not any change at all, in radon flux between more structured and less structured areas. And we see that, for example, on top deck. On the left is test pit 1. That's where we've got mesquite with lots of root structure down through the barrier. Test pit 2 is just grasses. It's a much more diffuse root structure, a lot less structural change within the diffusion, within the radon barrier, and the fluxes of radon are roughly about the same in test pits 1 and 2. We see similar things in 3 and 4. We'd be a little careful interpreting. We had some measurement problems in 4. But again, the fluxes, at least in 3, are not much different from what we found from 1 and 2. And then if we look on the slope, actually our fluxes were quite a bit lower on the slope than on the top deck, the 2 areas of the top deck. And on the top deck, we looked at 2 different areas of the top deck that had different amounts of structure, and yet we had roughly the same fluxes in the 2 different pits, 5 and 6. So one of the things that we see from these measurements, while we see a lot of changes in hydraulic properties due to petagenesis, we see a much more subtle effect for gaseous transmission. And actually that makes sense because our hydraulic properties are advection-driven processes where we're driving flow through the largest pores, and where our gas transmission processes are diffusion processes, and they're driven largely through some of the finer pores that are water saturated. Our large pore structures that we develop through petagenesis really don't affect the diffusion coefficients of these materials, the gaseous diffusion coefficients, in a very significant degree. Next slide. And again, I showed you this. We did see structure in these. So while we didn't see a large change in flux, we did see a good bit of structure. And we saw things like this root going right down through the tube. Next slide. If we look at scale effects, one of the things we saw in the lab, we saw a graph that looked a lot like this. This is a normalized flux of the flux relative to the average, just as a function of size. And so we were thinking that as we got a bigger measurement, we might see a higher flux because we are capturing essentially a larger network of pores. But we see essentially on average the flux stays about the same with scale. Again, it's a diffusion-driven process, not driven by the largest pores. We did find, and this one you have to cross your eyes a little bit to follow the trends. That's why we put in a log scale, 2 log scales. You can't get a good trend with 1 log scale, you use a double log scale. Right? But the variability, and we found this in the lab where we had more control conditions, as we got to a larger measurement, there was less variability. There wasn't a scale bias, that there wasn't a systematic change in flux with scale, but the variability changed reduced as we got a larger measurement, which makes sense because we just have more spatial averaging. So it's pretty consistent with what we'd expect. A couple more slides. One of the things that we did find, which was really interesting, is we compared our activated carbon measurements in the field to what we got from the alpha tracker. And you really get very different fluxes from an activated carbon than you get from an alpha tracker. And that's illustrated here in this graph. This radon concentration versus time from different test pits. The open symbols are what we get out of our alpha tracker. The green, the solid symbols are out of the activated carbon. The activated carbon, you put it in the flux chamber, you close it off, and about a day later you open it back up, you take the can out, you seal it up and send it to the lab. It represents cumulative radon absorption onto that activated carbon. And we know that as a question that came up early on, we've changed the boundary condition. So it's that early flux that's really the flux of interest is quite a bit different than the flux at 24 hours. And so if we take an aggregate measurement here at 17 hours or 24 hours later, we get something very different than what we would get from an alpha tracker. There's also some bias in the activated carbon measurements, which I think are due to some mass transfer limitations of radon getting into the pore space of the activated carbon. We haven't proven that yet, but I believe that's the mechanism. We've corrected these for relative humidity, by the way, so it's not a water molecules obscuring the absorption site. So what we found is that roughly the activated carbon measurement gives you a flux that's about half of what the alpha tracker will, and I believe that's a pretty reliable downward bias. It's probably about half of the actual flux. That's been an interesting lesson from this. Next slide. I think I'm at the end. Okay, yes, I got a couple of animations. So you can see that's actually the flux of interest, and one more. And when we calculate the flux from the activated carbon, we use that final measurement. We miss all the early time data, which is at a much higher rate, which is really what's of interest. And it gets back to that boundary condition issue when you put a chamber on it. So the way we go about making radon flux measurements in the future probably needs to employ some of these more time-dependent techniques with an alpha tracker so that we capture that flux process more realistically. Go ahead, one more. So some conclusions. We have reliable and practical methods now to measure this in the field. We're seeing petagenesis occur in barrier systems. We'd expect that. We see lots of other data on that. And we expect this not only at tailing sites, but other sites as well. And we predict that, and we feel confident in our ability to understand that and build it into PAs. We see it does affect the hydrology significantly. We know that, but we don't see it in the same thing for radon diffusion. The diffusive property, one's a diffusion-controlled mechanism, and one's an advection-controlled mechanism. And that's actually a very favorable finding. That makes at least takes out one more complicating factor in the performance assessment, you might say. And then the bias in the radon flux is one of the things that we've found is that roughly about a factor of 2, bias too low with activated carbon. So we have to revisit whether we want to continue to use activated carbon for these type of measurements or put in some type of correction factor. One thing I haven't shown, because we're still working on here today, is a comparison of the radon fluxes directly that they measured right after construction of the radon barrier, which they measured with activated carbon 20-some years ago, and what we measured last year. And we're not quite done with that. But all those numbers are roughly in that kind of 10 picocuries per meter square range, so which is pretty consistent with what we observed. So we're not quite ready to present that, but what we've seen is that it seems pretty consistent with what we found. And we start comparing the data at construction to what we're seeing today. The fluxes aren't changing in any considerable degree, largely because they're diffusion controlled. And I don't have that data available to present, but maybe next year we'll be able to show. So, all right, and there's lots of folks working on this. So I wanted to say again, repeat, this is a very collaborative effort. NRC, LM, EM, all working together to understand this issue, to kind of push the science forward so that we can incorporate these factors into PAs in a thoughtful way. And on the right's the key players on the project team. All right.
Thank you, Craig. Yes. So Dave has a question. And then we'll have Craig.
Greg, very nice presentations and examples that you have shown. As I'm a little bit familiar with some of the things that you have shown. Thing is that I have a couple of questions actually. You showed very nice slides on pedogenesis. Pedogenesis, yeah, but I think as far as I know, these sites are pretty not that very old, or 5 or 10 years, something like that. And the pedogenesis is not a very aggressive process or whatever process, but you have seen a very aggressive root vegetation and everything going on. I wonder after 10 years from now, the pedogenesis and all these activities will be so severe, or if you don't maintain, it will be so much. I think the phenomenon that you are observing, the release of radon, and then you're also talking about part of it goes in diffusion and part of it is these things. I don't know how far it will valid a valid concept. I wonder if there will be a free release to the atmosphere or something like that, because with a lot of, that's one of my observations. I don't know what you say about that. I have a couple of follow-up questions.
Well, I think one question is essentially, we've got a window in time where we've got some information. Does that really reflect the long term? I'm only 54, so I got like 20 more years to work. So we want to continue to figure this out.
Good.
We're not.
But
One of the things that we have found is there's the geomorphologists have worked on this with us over the last 15 years or so, are really kind of interested in how rapidly these changes occur at the near surface, because they're more rapid than a geomorphologist would traditionally think. But one of the things that we find is a lot of the change occurs early on, and then it gets into a fairly steady state condition. Now, steady state in the near term, may be for 100 years. And we start looking at 1,000 years, we've got geochemical processes and things like that we probably need to factor in. But that's why we want to look at the analogs. That's not something I talked about today. But when we looked, for example, at Falls City, when we did the work at Falls City, we also went into a soil profile that had the same, essentially, attributes as the cover. And are studying the structure in that and the hydraulic properties and the diffusive characteristics of that soil profile. And that's a profile that's more than 1,000 years old, more than 5,000 years old. And so we can make at least connect that dot from year 30 to several thousand years based on that analysis. And we'll have more of that. We're working on that right now. So I think analogs provide a really good clues. But the one thing we have found is things evolve quickly and then they kind of settle in. And nature does a lot to we engineer things. Nature pushes them back to where she thinks they should be, and then they sit that way for quite a while. That's at least what I'm seeing consistently. We're still exhuming sites. And I think our ability to continue to collect data and refine our knowledge is important. We just started a project a few years ago where we've got a 50-year agreement to do monitoring on it. 50 years. So I'm going to be out there just getting along. But to do that, monitor the hydrology and look at these changes for 50 years systematically. And we need to continue to do these things. That's important investment in building confidence in the predictions in our performance assessments. So I don't know if I got directly at
you address. You have got analogs and another thing is design the way you design some of those sites. And one of the sites you said that 80% saturation, and that helps suppress any radon flux going to the next layer and blah blah blah. 80% is a pretty good saturation, and in spite of that, I see all those layers and these things. You are seeing those radon flux, and if the radon comes, one thing is that I think you can probably modify that 80% to, or thickness, increase the thickness and something like that. This all design counter.
You could design around it.
Design one. And then no matter what, you're seeing the radon flux coming to the, coming out, and you said that cover and how we collect the samples. Is it possible from design point of view, similar to any landfill where you put a secondary liner and tertiary liner, you collect the whatever water collects. Similarly, you collect the radon flux from the top of the just the
leak
concept.
Detection zone. You can tell somebody to do that. I'm not going to tell them to do that.
Okay, thank you.
Right.
That's one of those things.
We'll have to have a bigger budget in all of our. If we're going to do that.
All right, John.
John talks to Neptune. fellow UT grad.
Yeah. John and I were in grad school together.
Yeah. You didn't say, but I assume you're talking about radon 222 here when you're looking at stuff. Okay. And I was really surprised by the results of petagenesis, or what I like to call naturalization of the cover, that it actually didn't affect the radon flux. So it'll be interesting to see how that plays out when you're out teetering around with your walker on these things in another 30 years. But I wanted to suggest one thing, and I take back what I said about modeling, because it's not just fantasy world. In fact, from modeling radon flux through covers, I discovered something that may provide a suggestion for some information to gather during your research. Is when a radon barrier is not a radon barrier, is when it's highly saturated, although that inhibits the migration of radon itself. Radon parents, of which the uranium mill tailings are full, especially radium-226, can migrate and diffuse through the liquid phase. And the wetter it is, the better for that. And so it can do an end run around the radon barrier and migrate through as radium and then turn into radon once it's through. So I wonder if you might take samples as you go through, or look to see, and it's probably after a couple decades isn't maybe long enough to see much effect, but after a long term, the radium itself, maybe there's no radium barrier that's in part of the system, and I wonder if that's something that has occurred to you, or if you might integrate into your studies.
That's a good idea. The diffusion coefficients in the liquid phase are always a lot lower,
Right.
but not zero.
Right.
One of the things we did do is we're looking at lead-210 that's sorbed on the solid phase to get a sense of this cumulative radium essentially migration across the barrier. Some of it would be from the liquid phase as well, potentially, right? Could have been in the liquid phase, and if it's...
You mean the source of the lead-210?
Yeah, potentially, right?
Yeah, since it's in the tailings, then it could migrate up, but it also then is being deposited by the radon as it goes, which is often a coupled process that is completely ignored in performance assessment, because people do their radon calculations separate, using a different piece of code or different equations, and they don't realize that it's leaving all this lead-210 behind. It gives you a nice external dose when you're walking around on the site.
Yeah, so we've got these profiles of lead-210 on the course. So maybe we could
interesting proxy perhaps for radium, or put radium in the suite of things that you look for.
Yeah, as essentially it's absorbing out of the liquid or the gas phase. I didn't think about the liquid phase till today, so I got to go back and work on that a little more.
Greg Flax, Savannah River National Lab. Craig, you noted much lower radon fluxes in the side slope where there was riprap, and I'm wondering, do you think that's because of the lack of vegetation on the side slope that led to higher infiltration and therefore a more saturated and effective radon layer? And if that's the case, would you recommend you just go with riprap for the whole design?
Yeah, that's a good question. I actually, there's about the differences side slope versus top deck. I think it has more to do with the activity of the tailings that were on the periphery than in the middle, to be honest with you. But one of the things that we do see, the covers that have rock covers where we manage the vegetation and prevent it from occurring do tend to create a high degree of water saturation in earthen barriers below. We've been monitoring test facilities at the Cheney disposal facility for more than 10 years now. And we have a side-by-side test section, one all rock, where we herbicide, spray it, keep all the vegetation off. Another where we're allowing it to naturally evolve. Very different hydrology in the layers below. And so that rock layer can actually be, from a gas flux perspective, can be very protective because it brings all the water in and it keeps that underlying system wet. Of course, we'll have the other radium diffusing up more quickly. So things are always more complicated than you expect. All right.
All right. I think, this definitely generates a lot of interest, and we'll have Craig, join the panel discussion.